We now take a look at a situation where we use inferential methods to test the equality of three or more means. So instead of just comparing two groups, we want to compare more than two groups, right? Three or more. And so to do that, we do something called an ANOVA test. And what we use that for, like I said, is to compare to see if the sample means come from populations, right? If the samples come from populations with different means. ANOVA stands for analysis of variance. And what we're looking at, is there a variation, right, between, we're comparing the variation between samples and within samples. And to give you an idea what I mean, but let's take a look at just some dot plots here. Here are some dot plots of the daily high temperatures of different cities, and you can see the distribution here. You can see kind of the centers. They're normally distributed, and so the centers are kind of in here, here, and here. And so based on that, does it look like one of the cities is different than the others, right? Or the population, right? So the sample temperatures, right? The means different from city to city. And so an ANOVA test to see, are the means equality, or is at least one of them different? And again, here we like to, for an ANOVA, we can look at a visual. Another way to look at another example would be if you're comparing restaurants. Here's the distribution of stars for a restaurant, right? 1 star, 2 star, 3 star. And so you can see the means are here in the middle, right? And then you can see the variation, what we talk between or within. And so when we talk about this between, variance between and variation within, within means we're looking within the same group. This one has small variation within. This has larger variation within, kind of looking at the standard deviation. Although the test is comparing mean values, right? We look at the variations within, and then between, so you can kind of looking at where their middles are and look at the variation here. Looks like these have different variations between them, right? Their means look a little different. Here, the variations between them look almost like their means, their centers around the same. And that's the idea we're talking about. And that allows us to measure, again, or do this analysis of variance. And of course, we're going to use statistics or technology to do this. It's a lot of calculations by hand to calculate those values. And so you can see you have a process, though, that we use to do this analysis of variance. Of course, you're going to define what our parameters of interest are. A hypothesis, right? The hypothesis is that the means are equal to each other, and the alternative is that at least one is different. And so we march down the same way with a hypothesis test here. ANOVA is a hypothesis test. We just have a different test statistic, but we still have to look at requirements, right? Each samples are independent from each other, simple random sample. And then we have these here that are hard to verify in our cases here, especially without the technology, but the populations that we're comparing are normal approximately, and that they have similar variances, or like when we analyze the standard deviations, we're looking at the variance. But again, hence that term, analysis of a variance here. And so we're going to go ahead and use StatCrunch or ArtofStat to do our calculations. And then we come to some typical conclusions here. And so we have conclusions. Again, once you do the calculations, we'll look at a p-value of the test at what's going to call an F statistic, which we'll look at in the next piece. But again, we have those conditions. If it's less than alpha, the p-value, or greater than alpha, we then reject or fail to reject. But again, it's important to acknowledge, what are we actually testing? What are our null and alternative hypotheses? That's what we're trying to do.